Hi Year 13 and welcome to this video on Lewis structures. In this video we're going to recap what molecules are, why atoms bond to each other, and what Lewis structures represent and how we go about drawing them. So first of all, what are molecules? Molecules are when you have two or more non-metal atoms covalently bonded together. Covalent bonds means electrons are shared between those two molecules, and non-metal atoms mean we find them in the top right-hand corner of the periodic table. So why do atoms bond? If we had these three atoms like this, they are in an unstable configuration, meaning none of them have a full valence shell. Hydrogen has one electron in its valence shell, and that shell can hold two, so it's not full and it's unstable. Phosphorus has 5 electrons in its valence shell when that shell could hold 8, so it's also unstable. If we bond the hydrogens to the phosphorus in this way, then phosphorus has 8 electrons around it, which is a full valence shell, and each hydrogen has 2 valence electrons around it, which is a full valence shell. So as you can see, drawing these kinds of diagrams shows which electrons belong to which atoms and how can we design a potential structure that satisfies every atom and gives them a stable configuration. So let's go through the process for drawing Lewis structures. The steps for drawing Lewis structures are: first, count the total number of valence electrons in the molecule. So for each of the individual atoms, how many valence electrons does it have? Second step, identify the central atom. The central atom will usually be the one there's only one of in the molecule. So for example, in our pH3 example from before, there was only one P. Therefore that was our central atom. If you have multiple options, pick the least electronegative atom. That will typically be your central atom. Third step, draw a structure connecting the atoms with a single bond. And a reminder that a single bond contains 2 electrons. A double bond contains 4, a triple bond contains 6. Fourth step, put the remaining electrons around outer atoms first, then the central atom, so that all atoms have a full valence shell. Fifth step, trial and error, using double and triple bonds. Only do that fifth step if you have not drawn a satisfactory structure after the first 4. Let's use those rules and look at a couple of examples. First, NH3. Nitrogen has an electron configuration of 2, 5, meaning it has 5 electrons in its valence shell. Hydrogen has an electron configuration of 1, so it has 1 electron in its valence shell. We have 1 nitrogen, but we have 3 hydrogens, so that's going to give me 3 valence electrons from the 3 hydrogens, giving me a total of 8 valence electrons. That's step 1 complete. Step 2, identify the central atom. There'll be only one of this, so that's going to be our nitrogen, meaning our hydrogens will be all around. Step 3, draw a structure connecting atoms with a single bond. You can choose to draw 2 dots for your single bond, or you can draw a straight line. Step 4, put the remaining electrons around the outer atoms first. Well, each of my hydrogens has 2 electrons. The 2 electrons in the bond belong to both atoms. So this hydrogen has 2, this one has 2, this one has 2, therefore the hydrogen's valence shells are full. Then put the remaining electrons around the central atom. So if I've used 2, 4, 6, my last 2, giving me 8, go around my central atom. I've used all 8 of my electrons. Hydrogen has full valence shells with 2, 2 and 2. Nitrogen has 2, 4, 6 and those 2 makes 8. Everybody has a full valence shell, everybody's stable, no need to trial and error with double bonds. Move on to the next example. SO2. Sulfur has an electron configuration of 2, 8, 6. Giving it 6 electrons in the valence shell. Oxygen has an electron configuration of 2, 6, giving it 6 electrons as well. We have 2 oxygens, therefore my total will be 6 there and 12 there, gives me 18 valence electrons. So let's start off by looking at one possible example. Central atom is going to be sulfur. There's only one of them. So my S can go in the middle, O on either side. Start by connecting the atoms with a single bond. Fill the outer atoms first. Okay, so now that oxygen has got 8 electrons around it, 2, 4, 6, and 2 from the bond is 8. This oxygen's got 2, 4, 6, 8. So I've used 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. I have 2 left, put them around my central atom. Does everybody have a full valence shell? Oxygen, yes. Oxygen, yes. Sulfur, 2, 4, 6. No. So this is not the correct Lewis structure. Therefore we will need to trial and error using double bonds and triple bonds. So let's try again. I'm going to start by having 1 double bond and 1 single bond. Fill the outer atoms first. This oxygen's already got 2, 4, so give it 4 more. This oxygen's only got 2, so it needs 6 more. How many have I used? 2, 4, 6, 8, 10, 12, 14, 16. The last 2 can go around the central atom. Is this the correct Lewis structure? This oxygen has 8, yes. This oxygen has 8, yes. The sulfur now has 8, yes. So everybody has a full valence shell, everybody's stable, and I've used all 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that is the correct Lewis structure. Now let's consider polyatomic ions. Polyatomic ions are effectively molecules that have gained or lost electrons to become charged. There are 2 types of polyatomic ions, cations and anions, depending on whether they have lost or gained electrons. Anions have gained electrons, so all we need to do when drawing the Lewis structure of an anion is add extra electrons equal to the charge. So let's have a look at some examples here. OH minus. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. However, because of our charge, having a negative charge means it's gained 1 electron, so we need to add 1 extra, giving us a total of 8 valence electrons. Go through the process. There's no real central atom here, but it would be the oxygen if it were to be one. Connect them with a single bond, fill the valence shells. Hydrogen's got 2, so it's satisfied. Oxygen's got 8. I've used 2, 4, 6, 8, so every atom is stable. To show that this is a polyatomic ion, I need to put square brackets around the Lewis structure and show that it's got a charge. Our second example, NO2 minus. Nitrogen has got 5 valence electrons. Oxygen has got 6 valence electrons, and there's 2 of them. And the charge gives us an extra 1, meaning we've got a total of 18 valence electrons. So drawing the Lewis structure of this polyatomic ion, why don't you pause here and have a go. Hopefully you landed with a Lewis structure where nitrogen is the central atom, a single bond and a double bond, filling the valence shells. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. Oxygen's got 8, oxygen's got 8, nitrogen's got 8. To show it's a polyatomic ion, square brackets and a negative charge. Now having a look at cations. Cations, we remove electrons equal to the charge because cations have lost electrons to have their positive charge. Let's have a look at these 2 examples. H3O plus. H has 1 valence electron and there's 3 of them. Oxygen has 6 valence electrons, and due to the charge we need to remove 1 electron. So there's 3 plus 6 is 9, but take away 1 leaves us with 8. Draw a possible structure. The central atom, we're going to pick our O because there's only 1 of them. Put the hydrogens all around. join the atoms with a single bond. That fills the valence shells of all my hydrogens. I've got 8 electrons to use, so put the last 2 around the central atom, and full valence shell with 2, with 2, with 2. Now oxygen's full with 8. I've used the correct number of electrons, 2, 4, 6, 8. I need to put a square bracket around with a positive charge to indicate the charge on my polyatomic ion. Coming across to NH4+, nitrogen has got 5 valence electrons. Hydrogen has got 1 valence electron, and there's 4 of them. And the charge means I need to remove 1 electron, giving me a total of 5 plus 4 is 9, minus 1 comes back to 8. Why don't you pause here and have a go at doing this polyatomic ion Lewis structure. Okay, let's have a go. So nitrogen is my central atom, there's only 1 of them, 4 hydrogens around it. Join them all with a single bond, and that's got 2, that's got 2, that's got 2, that's got 2, so all my hydrogens have a full valence shell. This nitrogen has 2, 4, 6, 8, so it has a full valence shell. I've used 8, 2, 4, 6, 8. So everyone is satisfied. So now I need to put my square brackets around and put the charge on, and that is the correct Lewis structure for the ammonium ion, or NH4+. Let's take a look at molecules that do not obey the octet rule. The octet rule is simply that atoms will lose or gain electrons or share electrons to get a full valence shell with 8 electrons. So hydrogen, we know, is an exception to this rule because its valence shell can only hold 2, and there are more exceptions, which we'll now look at. Electron deficient molecules. These molecules include atoms that are stable with less than 8 valence electrons, such as beryllium and boron. They can have fewer than 8 and be stable. Let's look at 2 examples. Beryllium has 2 valence electrons. Chlorine has 7, and there's 2 of them, giving me a total of 16 valence electrons. So if I draw my beryllium as my central atom, and 2 chlorines either side, join them with a single bond, fill my outer atoms first, and that is a finished Lewis structure. Even though beryllium only has 4 electrons around it, it is stable in that configuration. So that is the correct Lewis structure. Beryllium is happy to only have 4. For BF3, boron has 3 valence electrons, fluorine has 7, and there's 3 of them, giving me a total of 21 there plus 3 is 24 valence electrons. So, if I draw boron as my central atom and 3 fluorines around, connect them with a single bond, fill the outer atoms first to give all of these fluorines a full valence shell with 8 electrons. So fluorine's got 8, 2, 4, 6, 8. Fluorine's got 8, 2, 4, 6, 8. Same with this fluorine. Boron's only got 6, but I've used all 24 of my electrons. 8 and 8 and 8 makes 24. And boron is stable, having only 6 valence electrons. So boron is okay with 6. That is a correct Lewis structure. So you need to remember that beryllium is okay with having 4, boron is okay with having 6. Or another way of saying that is beryllium is okay having 2 electron pairs, boron is okay having 3 electron pairs. They are stable in those configurations. There are also some molecules where you can have an expanded octet, or more than 8 valence electrons. This typically happens with atoms in the 3rd row on the periodic table. They are the ones that can have more than 8 valence electrons around them. So let's consider this example of PCl5. Phosphorus has 5 valence electrons. Chlorine has 7 valence electrons, and there are 5 of them. So my total is going to be 7 5s are 35, plus 5 more makes 40 electrons. Phosphorus will be my central atom because there's only 1 of them, and I now need to draw 5 chlorines around my central phosphorus. So I try to spread them out somewhat evenly. Connect atoms with a single bond, and just by doing that, our phosphorus has got 2, 4, 6, 8, 10 around it. But because phosphorus is in the third row of the periodic table, it can have an expanded octet, and it's okay with this configuration. The reason for that is those extra electrons can slot into the 3D subshell, which is the same distance from the nucleus as the 3p, to which it would normally be bonding in this area. So now we fill our outer atoms to make all them have 8. Chlorine has 8 times 5, means I've used all 40 of my electrons. Phosphorus has got 10. That's okay because it's in the third row on the periodic table, meaning it can have an expanded octet with more than 8 valence electrons, and that is the correct Lewis structure. Why don't you have a go at this one here? Draw the Lewis structure for SF6. Pause the video and have a go. So, sulfur has 6 valence electrons. Fluorine has 7 valence electrons, and there's 6 of them. 7 6s are 42, plus 6 is 48 electrons to use in our molecule. So my central atom will be sulfur, because it's the one there's only one of. I need to have 6 fluorines around. Connect all with a single bond. This is when it really helps to use lines for a bond, because to try and draw all your electrons around there can get quite messy. Fill all your outer atoms. And check. Fluorine has 8. All of them have 8, so all the fluorines are stable. Sulfur has 2, 4, 6, 8, 10, 12. That is more than 8, but again, because it's in the third row of the periodic table, it is okay to have an expanded octet. Those extra electrons have slotted into the 3D subshell. So this is the correct Lewis structure for SF6. Why don't you have a go at this polyatomic ion, CO32-. Pause here and have a go. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, and there's 3 of them. And because of the charge, I get an extra 2 electrons. 4 and 2 is 6, plus another 18 gives me 24 electrons total to work with. My central atom will be carbon, with 3 oxygens around it. Start by joining with a single bond. Fill the outer atoms first. Check, that's got 8, that's got 8, that's got 8. This has only got 6. How many electrons have I used? 8 there, plus 8 more is 16, plus 8 more is 24. So I've used all my electrons, all the oxygens are full. Carbon's only got 6, therefore this is not the correct Lewis structure. Try again. This time I'm going to have a double bond. Oxygen's got 8, oxygen's got 8, oxygen's got 2, 4, 6, 8, so that's 8 as well. Carbon's got 2, 4, 6, 8. So everybody's got a full valence shell, and I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that is the correct Lewis structure. I now need to add my square brackets and give it a 2 minus charge. And that's correct. Why don't you now have a go at POCl3. Pause the video here. Phosphorus has 5 valence electrons, oxygen has 6 valence electrons, chlorine has 7 valence electrons, and there's 3 of them. Adding all them together, 5 and 6 makes 11, there's 21, 11 and 21 makes 32 valence electrons. Phosphorus will be my central atom, O, Cl, Cl, Cl. Join them with a single bond. Fill the outer atoms first. and I've used 8, 8, 8, 8, makes 32, so I've used them all, and they've all got full valence shells with 8, phosphorus has full with 8, so that is the correct Lewis structure. What you could also have done is moved a pair of electrons into this double bond, so you could have drawn this as being a double bond. That would also be a correct Lewis structure, because the phosphorus would have 10 electrons, which it's allowed to have being in the third row of the periodic table, and the oxygen would still have 8, which makes that also in a stable configuration. So you could have drawn a double bond, both structures would be acceptable. I hope you found this video on Lewis structures helpful. See you in the next one.